Hi, I'm going to be talking about writing out DOMsday toward detecting and preventing DOM cross-site scripting vulnerabilities. Cross-site scripting vulnerabilities are the most frequently reported type of web vulnerability, accounting for 25% of all web vulnerabilities. And I'm going to give you some background about cross-site scripting vulnerabilities in general at a high level. And we have a user and a website with a vulnerability. And an attacker can craft an exploit, for example, like a malicious link, that may cause the user to visit a page, and the website returns a exploited page with the attacker's script inside of it, and then the browser executes the attacker code. And so here, the attacker can do anything that the user could on the website. Now, DOM cross-site scripting is a case of cross-site scripting vulnerability where the vulnerability is entirely inside the JavaScript that's run in the browser. So for example, here is a short example of a simple DOM cross-site scripting vulnerability where the part of the URL is concatenated with markup and then injected into the page. Now, current client-side defenses for DOM cross-site scripting are often inadequate. So for example, content security policies are often not configured for websites, or when they are configured, they might be improperly configured so that they don't stop these types of attacks. Web application firewall filters are easily bypassable by attackers in many cases. And so a more promising solution is to detect vulnerabilities ahead of time and then fix them. And so the state of the art for this is using taint tracking to recognize vulnerable flows of attacker controlled information to these sensitive functions that are capable of executing code. And so in this work, we firstly improved the methodology for recognizing vulnerable flows using taint tracking. So taint tracking can tell you where a potentially vulnerable flow is, but for a variety of reasons, it may not actually be vulnerable to an attack. So so it's important to recognize actually vulnerable flows because programmers could sanitize the input arbitrarily. So secondly, we studied the prevalence of DOM cross-site scripting in the real world and compared our measurement of DOM cross-site scripting to past measurements to see if the internet has changed over this time period. And thirdly, we wanted to see whether static analysis tools might be able to detect some of these vulnerabilities ahead of time, so it might be easy for an engineer to run their code through a static analysis tool that could detect these vulnerabilities before code is pushed to websites. And so DOM cross-site scripting attacks exist when there's a flow from attacker controllable information to a sensitive sync function. So I've mentioned vulnerable flows, and I want to explain what I mean by that. So here's an example where the document's URL is concatenated with markup and inserted into a sensitive sync function. The flow goes through the URL and then the markup variable, which ends up as an argument to document.write. And so what we're trying to do is identify these flows from these sources. So like these are things that an attacker could potentially have some control over, like the URL of the document, cross-origin messages, the refer. And we're trying to identify flows of that information to these sensitive sync functions that are capable of executing code. So like document.write, assigning to the inner HTML, or using eval. And so the taint tracking infrastructure that I'm going to talk more about later will keep track of the provenance of each of these strings. And so here, this is where the flow is going through. And so in some cases, a potentially vulnerable flow may not actually be vulnerable because of specific encoding functions that are used inside the flow. So these encoding functions would render an attacker unable to inject arbitrary code. So for example, here the encode URI function encodes the input and makes it so an attacker would be able to inject arbitrary JavaScript. The encoding function escapes characters that would be able to indicate that a script would be run, and instead interprets it as a string. And so I said we detect vulnerabilities using taint tracking, and the specific way we did that is we modified Chromium's JavaScript engine to attach taint information to strings. And so I'm going to go into some detail about how that works. And so the design of this is based off of Leckies et al.'s previous work. And so each byte of the string contains 1 byte of taint information that's associated with it. And this taint information indicates where the data came from for that string, and whether it's the source of the data for that string. So we differentiate between different sources. And we also keep track of the different encoding methods that have been applied to that string. So here I'm showing zeros as untainted and t's as tainted, but in reality, there's more data that's associated with each byte of the string. And so during execution, these taint bytes are propagated throughout the program. So for example, when concatenating an untainted string with tainted strings, those tainted bytes are also concatenated. And so this was a lot of engineering work to modify the V8 JavaScript interpreter and to make it so that the taint bytes are propagated and that there's no crashing when things jump into JITted assembly code. And Ben Stock is nodding. And so the taint tracking infrastructure watches for when this tainted data enters a sensitive sync function. And so when that happens, we log the code location of the call, the value of the tainted argument, and so the taint information of the argument, and some other auxiliary information about the scenario so that we can recreate this after the fact. And so the taint infrastructure that I just talked about identifies flows of potentially vulnerable flows of attacker controllable information. But for a variety of reasons, like I talked about earlier, they may not actually be vulnerable. And so there are many ways that an attacker could sanitize that data. And so we experimented with 2 different ways of confirming flows. And the first one is where we made a confirmation injection and appended an injection to the end of the URL. And so this gets situations where the entire URL is concatenated with markup. So for example, here, like the example I showed earlier, if we observe this flow happening and we observe that the URL tainted data entered this sync function, we can later create a new URL and visit the page again and observe if that flow still existed with our injection. And so if it did, that would indicate that an actually vulnerable flow. However, that method doesn't always confirm flows that are indeed vulnerable. So for example, here's a case where the previous method doesn't work. It grabs an argument from a query parameter and then concatenates that query parameter with some markup. And the previous method doesn't work here because the injected content is at the end of is in a query parameter and not at the end of the string. So in this method, we try to see exactly which bytes of the source make it into the sync function, and then replace those bytes with our injection. And so the intent of this new method is that it would allow us to confirm more flows that are actually vulnerable. And so now I want to talk about our results using this methodology. And I'm going to start with talking about our results for the prevalence of DOM CrossSite Scripting in the real world to validate our methodology. And so we started with 10,000 seed domains from the Alexa most popular websites. And on those domains, we sampled from the one link deep subpages and visited 45,000 web pages on those domains. And we observed 285,000 flows from URL sources to JavaScript and HTML syncs on those pages. And so this is a common category of exploitable flows that we're going to focus on for this. We then removed flows that we were sure were not vulnerable due to the encoding methods that have been applied to the strings. And we end up with 55,000 flows after that. And then we uniqued these flows to try to identify unique vulnerabilities. And so we uniqued the flows by the domain that we were visiting when we observed the flow, the URL of the script where the sync function is located, and the location in the script. And this is designed to remove duplicates that come from executing the same piece of code multiple times. So for whether on the same page or on different pages. And so of these 5,000 potentially vulnerable flows, some were confirmed using the add-end method and some with the in-parameter method, and some using both. And we found 700 confirmed with the add-end method, 1,000 with both methods, and 1,500 with the in-parameter method. And so this is a total of 3,000, a little bit more than 3,000 confirmed vulnerable flows. And we were able to confirm 83% more using this in-parameter method than just using the add-end method. And so this 3,000 vulnerabilities is the data set of vulnerabilities that I'm going to talk about for the rest of the talk. And so in our data set, we wanted to know how these vulnerabilities are distributed across different domains. So we have on the y-axis the number of bugs found on a domain, and on the x-axis the domain sorted by bugginess. And what we found is we found some very buggy domains with many bugs, and we also found a long tail of domains with one or two bugs. We also wanted to know how the vulnerabilities were distributed across different categories of websites. So on the y-axis, we have the category of website that we were visiting when we observed the vulnerability. And you don't have to read all of the vulnerabilities. The takeaway is that the most frequent category we observed were sites that host web ads and analytics. And so we wanted to know what's causing these vulnerabilities more qualitatively. And we observed most of them were simple concatenation without effort to sanitize data. So very much like the example that I showed earlier at the beginning of the talk. We also noticed some instances of custom HTML templating code that doesn't make effort to sanitize or encode any of the parameters to the templates. And we noticed some instances of ad hoc sanitization that's unlikely to stop a real attacker, but might stop some specific cases. So for this, we only sampled 20 websites from our data set and then manually looked at them. So we can't say anything too definitive about magnitudes, but about 2/3 of them were from this simple case. We wanted to know whether the prevalence of DOM cross-site scripting has changed over time. And so the state of web development has changed over time, and we wanted to know if DOM cross-site scripting vulnerabilities have been increasing or not. So we compared our results to a past study that looked at this, Lecky's et al.'s work, and tried to use the same methodology that they used in their study. And so that happened 5 years ago, and the numbers here that I'm going to show you are trying to emulate their methodology as closely as possible. And so what we found is we found more flows per page, almost twice as many. We found a larger ratio of vulnerabilities per page, almost 3 times as many. And we found a larger fraction of those flows were vulnerable. So we believe that this points that there may be an increase in DOM cross-site scripting vulnerabilities on the internet. And so the last thing I'm going to talk about is our findings about static analysis tools. And so, as I mentioned earlier, we wanted to know if static analysis tools would be able to help identify these vulnerabilities before code is ever pushed to a website. And so what we did is we sampled from our data set of vulnerabilities and checked if a few off-the-shelf tools would be able to find those vulnerabilities. And so we looked at 3 tools that we could afford, and 2 open source ones and 1 paid one. That is, the paid one was previously reported to have some comparable accuracy to other much more expensive tools in general vulnerabilities. And so what we found is that none of these tools found more than 10% of the vulnerabilities in our data set. However, so Burp Suite, the one that found 10% and had happened to have 0 false positives and found a few other bugs that we didn't find with our methodology. And the other tools had very high false positive rates. So it's likely that the static analysis tools aren't going to find many of these bugs that we found. And so in summary, we improved the measurement methodology for finding DOM cross-site scripting vulnerabilities, and this allowed us to find 83% more vulnerabilities. And we gained insight into the causes and distribution of vulnerabilities on the internet, and found that DOM cross-site scripting vulnerabilities might be increasing. And we also showed that static analysis tools are likely not to find many of these vulnerabilities that we found. And so I mentioned earlier that engineering the Chromium infrastructure to was a large part of this work, and so we open sourced our version of Chromium that does taint tracking so that it might be of use to other people. So thank you.
So I was curious when you looked at the example of injecting into parameters in the URLs, did you see, because oftentimes when we're talking about client-side JavaScript, they have much more freedom into how they parse parameters after the hashbang, right? Did you see any cases where they weren't using traditional URL parsing, they were doing some kind of other way of passing parameters?
Yeah, so most of the cases we saw were people doing ad hoc sort of URL parsing, implementing their own method of doing it and looking for like the question mark and then splitting on the ampersands and parsing the string that way. So that is a lot of the things that we saw.
Awesome. And then, so when's the end of DOMsday going to be about? Because you just scared us all. So when do we predict in the future that this will actually decrease?
When is the end of DOMsday? That's a great question. So I think that one of the things that would be necessary for that to happen is for there to be easily accessible tools for people to be able to find these issues on their own. And so we're hoping that releasing our infrastructure might foster some of that.
Awesome, great. Well, please
Thank
join
you.
me in thanking, don't thank me, thank the speaker, Billy. All right,